Today, I'd like to introduce a very important module, OSPF. OSPF is a representative example of one kind of dynamic routing protocol, the link state routing protocol. It is also the industry's most widely used IGP. Today, we're going to take a look at the basic concepts behind OSPF, before going over the establishment of OSPF neighbor relationships and its working mechanism, and then finally learn how to perform basic OSPF configuration. Let's first start with an overview of OSPF. Before we can really get to grips with OSPF, we should go over the basic concepts behind distance vector routing protocols. One of the characteristics of these protocols is that a router running a distance vector routing protocol floods its own routing table to other routers. The routers exchange routing tables and learn routes from each other. Note that routers exchange routing tables even though they are unclear of the entire network topology. We call this process routing by rumor. This is a defining feature of distance vector routing protocols. A link state routing protocol works completely different. Let's start by talking about the OSPF working process from the macroscopic, abstract perspective. All the routers running OSPF first establish neighbor relationships with each other. Subsequent OSPF operations are performed based on the neighbor relationships. Next, the OSPF routers will flood link state advertisements, LSAs. LSAs can be simply considered as information about the entire network topology, such as costs of directly connected interfaces, network segments, peer devices, and other parameters. These parameters help the routers understand the entire network topology. When OSPF routers send LSAs, they also collect LSAs and then store them in link state databases, LSDBs. An LSDB can be simply understood as a description of the entire network topology. After LSDB synchronization, OSPF uses the shortest path first, SPF algorithm. This algorithm calculates a loop-free tree structure with the local node itself as the root. The tree represents all the shortest paths originated from the local node and destined for all the other nodes in the topology. The SPF algorithm is the core of the OSPF protocol, which ensures that the calculated routes are loop-free. This is because the routers have a comprehensive understanding of the entire network. Finally, OSPF adds the calculated optimum paths in an LSDB to a routing table to generate route forwarding entries, which will act as the basis for forwarding data packets. This is a brief breakdown of the working process of OSPF. Now let's go over the differences between link state routing protocols and distance vector routing protocols. First, a distance vector routing protocol updates routes by rumor. Second, Routing Information Protocol, RIP, can run after the protocol has been activated on an interface. There is no need to establish a neighbor relationship for RIP. Third, RIP is not able to understand the entire network topology, which can easily cause a loop. To resolve loop problems, RIP defines anti-loop mechanisms, such as route poisoning and poison reverse. OSPF uses the SPF algorithm to prevent a loop from the ground up. OSPF stands for Open Shortest Path First, which means that it is public and any vendor can use this protocol. This is a major reason for its wide application. OSPF is used widely, supports large-scale networking, and converges rapidly. OSPF uses the SPF algorithm to prevent loops, but loops may still occur in complex networking. OSPF defines the area concept, which makes the network layout more scientific and supports networks of larger scales. OSPF also supports equal cost routes and hierarchical routing. It supports verification to enhance security. In addition, OSPF sends packets in multicast mode. It has two multicast addresses, 224.0.0.5 and 224.0.0.6, which are exclusively reserved for OSPF. Next, I'd like to introduce some terms related to OSPF. The first is router ID, which is the identifier of an OSPF router and is unique in the entire domain. A router ID is in the same format as an IP address. A router ID can be set in two ways. The first way is to manually configure the router ID for an OSPF router. In the second way, a router can obtain a router ID by OSPF. A router ID is not preempted. That is, after an OSPF process is started, irrespective of any changes in the interface IP address, the router ID will not change unless it is manually modified and the OSPF process is restarted. Each routing protocol has a parameter that measures a route's quality, which we will call metric. For example, RIP uses the hop count to measure a route's quality. However, when there are only a few routers with low bandwidth, RIP's measurement is not reliable. OSPF uses the cost as its metric to measure a link's quality. OSPF is an interface-sensitive protocol. Therefore, the cost is calculated based on an interface. It is calculated as 100 Mbps over interface bandwidth. Due to the continuous increase of bandwidth, 100 Mbps is only OSPF's reference bandwidth and can be modified as needed. Let's take the following figure as an example. The cost of R1's left interface, GE0/0/0, is 1. The cost of R2's left interface, serial 4/0/0, is 50. And the cost of R3's left interface, GE0/0/0, is 1. R1 puts the route destined for 1.1.1.0/24 in OSPF and advertises the route to R2 and R3. When R2 learns this route, the current cost is the sum of costs for the route origin and all inbound interfaces along the path. That is, 50 plus 1 equals 51. An interface cost affects a route cost, and a route cost affects route selection. As shown in the figures, R1 and R3 are connected to the same network segment, 192.168.100.0/24, and they both establish OSPF neighbor relationships with R3. Therefore, they both advertise information about this network segment to R2. In this case, R2 has to preferentially select a path. As shown in the left figure, the costs of the routes from R1 and R3 are the same, so they both can be used and are put into R2's routing table. If no fault occurs and we want traffic to be forwarded only through the path where R1 resides, we can change the cost of R2's right interface, GE0/0/1, to a larger value so that the left path will be preferentially selected and put into R2's routing table. OSPF uses three tables. The first one is the neighbor table. We have mentioned before that two OSPF routers have to establish a neighbor relationship before working. OSPF defines a series of state machines, and an OSPF adjacency is established correctly only after the OSPF routers both enter the fully adjacent state. After an OSPF router discovers a neighbor on the link, it writes the neighbor information to this table. OSPF requires that every two neighbors be directly connected. OSPF neighbors cannot be connected through other routers. When you troubleshoot a link failure, you can search the neighbor table for the OSPF neighbor and its status. The second table is the link state database, LSDB. An LSDB is used to store LSAs obtained through flooding, and it can be considered as a map for an OSPF router to know the entire network topology. The third table is the OSPF routing table. An LSDB uses the SPF algorithm to calculate loop-free tree reflecting the shortest paths. Then OSPF puts the shortest paths into the OSPF routing table. OSPF defines 5 types of packets. The first type is hello packet. As the name implies, hello packets are used to say hello between OSPF routers. In addition, they are also used to discover OSPF neighbors on direct links and establish OSPF neighbor relationships. Lastly, they are used to keep the neighbor relationships alive. The second type is database description, DD packet. DD packets are exchanged between OSPF routers after a full adjacency is established to synchronize information in the LSA header. The third type is Link State Request (LSR) packet. When a router receives a DD packet and is interested in information it does not have, the router will send an LSR packet to its neighbor for a request. The fourth type is Link State Update (LSU) packet. An LSU packet contains complete information about one or more LSAs. The last type is Link State Acknowledgement (LSACK) packet. An LSACK packet is used to acknowledge the LSA contained in an LSU packet to ensure reliable transmission. Next, let's get an overview of the OSPF neighbor relationship establishment process. Two OSPF routers do not know each other in the initial phase, and they both send hello packets. After they receive the hello packets from each other, a neighbor relationship starts to be established on a directly connected link. First, the neighbors exchange the summary information in the LSA header by sending DD packets to elect the DR and BDR. Then they request and send LSAs for synchronization. After the synchronization is complete, the neighbors enter the fully adjacent state. To view information about OSPF neighbors, you can run the Display OSPF Peer command. After this command is run, the neighbors discovered on all OSPF activated interfaces and the neighbor status are displayed. Focusing on the fields marked in red in the command output, Router ID indicates the neighbor's router ID, Address indicates the neighbor's IP address, State indicates the neighbor's status, and Full indicates the fully adjacent state. As previously mentioned, OSPF is an interface-sensitive routing protocol. Many OSPF operations are related to the network types of interfaces. OSPF defines various network types: P2P, Broadcast Multi-Access, BMA, Non-Broadcast Multiple Access Network, NBMA, and P2MP. This table lists the default network types of OSPF interfaces with multiple protocols running. On the MA network shown in the figure, multiple OSPF routers are connected to the same switch, and they are in the same broadcast domain. If OSPF is activated on the interfaces, they will send hello packets in multicast mode, attempting to discover other OSPF routers on the links. In the end, all routers will establish neighbor relationships with each other, and the total number of relationships will be n times n-1 over 2. The increasing number of routers also causes the rising number of neighbor relationships. Each router has to consume a large number of resources to maintain these neighbor relationships. Therefore, it is unnecessary to establish neighbor relationships between every pair of routers. Therefore, we define two roles: designated router (DR) and backup designated router (BDR). The DR is the leader on a network. The BDR is the secondary leader, and the other routers do not have a defined role. The others establish neighbor relationships only with the DR and BDR and not with each other. This greatly reduces the number of neighbor relationships and also reduces the number of LSAs to be flooded on links. The election of the DR and BDR depends on the information contained in the hello packets they send. First, the interface priorities of different routers are compared. The larger value indicates a higher priority. Second, if the interface priorities are the same, the OSPF router IDs are compared. Pay careful attention to the following aspects. 1. The DR others establish only full adjacencies with the DR or BDR and cannot establish neighbor relationships with each other. 2. The DR is not preempted. That is, if the OSPF process is started, the DR remains unchanged, even if a router's interface priority is increased. 3. The election of the DR and BDR is also based on interfaces. To be more precise, a router's interface can be elected as the DR. After the DR and BDR are elected, if the network topology changes and a router other than the DR or BDR detects this change, the router puts the topology change information in LSAs and then sends them to the DR and BDR. The router uses the reserved multicast address 224.0.0.6 to notify the DR and BDR. After receiving the change, the DR uses the multicast address 224.0.0.5 to notify the other OSPF interfaces of the change. We can regard a series of routers running OSPF as one domain. If there are no defined areas in this domain, routers in the same AS have to synchronize their LSTBs. In this case, each router's LSTB becomes increasingly large. In case of another network change, the LSTBs have to be synchronized again, consuming excessive resources. To resolve this issue, we divide a domain into different areas. A domain contains one or more areas. Each area can be identified by a decimal number or an IP address in the dotted decimal notation format. Only intra-area routers synchronize their LSTBs, which minimizes the LSA flooding scale. We can flexibly plan areas. However, if we want to deploy multiple areas, there is only one backbone area, Area 0, which is used to connect all the non-backbone areas. Additionally, all the non-backbone areas must be directly connected to the backbone area. After a domain is divided into multiple areas, the OSPF routers in these areas have different roles. OSPF routers in common areas are called internal routers, while a router belonging to both a backbone area and a non-backbone area is called an area border router, ABR. An ABR can be used for route aggregation and packet filtering. A router in Area 0 is called a backbone router. The last one is AS Boundary Router, ASBR. An ASBR connects to the OSPF domain on one end and to another AS on the other end. Last but not least, let's look at basic OSPF configuration. Basic configuration includes two steps. 1. Creating an OSPF process. 2. Activating OSPF on involved interfaces. The first step is to create an OSPF process and specify the process ID. You can optionally specify a router ID. After entering the OSPF process, enter a specific area and activate OSPF on the involved interfaces. Specify an area ID and then run the network command to activate OSPF. A wildcard mask and an IP address are specified in pairs. However, a wildcard mask and a subnet mask are different. In a network mask, the bits that are 1 second indicate the network ID. In a wildcard, 0 means that the equivalent bit must match. As shown in the figure, the IP address is 172.16.1.0, and the wildcard mask is 0.0.0.255. Convert them into binary representations. 0 in the wildcard mask indicates that the equivalent bits must match, and 1 indicates that the equivalent bits do not matter. Among the 3 IP addresses shown in the right figure, only the first one is matched, and the interface with this IP address will be activated with OSPF. OSPF will not be activated on the other 2 interfaces. Now let's look at an example for configuring a single area. On the network shown in the figure, 3 routers in the backbone area are connected to 2 PCs. The entire network must be interworking. First, configure R1. Specify the OSPF process ID to be 1 and router ID to be 1.1.1.1. Enter Area 0 and run the network command to configure the 2 network segments to belong to Area 0. After the configuration, OSPF is activated. The configurations of R2 and R3 are the same as R1's. Pay attention to their own router IDs and network segments of different interfaces. Now let's come to the basic configuration of multiple areas. Based on the previous single area configurations, we need to perform special configurations on the ABR R2. We need to configure the network segments of R2's different interfaces to belong to different areas. The network segment 192.168.12.0 must be configured to belong to Area 0, and the network segment 192.168.23.0 must be configured to belong to Area 1.